we're going to start with Newton's first law. Can you tell us Newton's first law in the equation form?
Yes. Delta F is 0.
And can you tell us Newton's...
Delta!
I was thinking of some momentum. Okay, come
all right, so I'm going to just write it down what he said. He said,
What a stupid guy!
No. That's what he meant. All right, sigma f is 0, okay. And then next one. What is the next one? What is my other marker?
This one?
Actually, this one doesn't work. Oh, yeah, the markers are here. Okay. Isaac, can you tell me Newton's first law? Explain, describe.
What Newton's first law basically says is that sigma F is equal to 0, which means that the total net force on an object is equal to 0. In other words, that object might not have anything acting on it at all. It might have one force that's canceled out by another force, whatever. If the total net force in no direction is 0, then that means that the object will keep a constant velocity. What that means is that it's not going to accelerate. It's not going to turn around or change direction. And if it's at rest, it will stay at rest until an unbalanced force acts on it.
Yeah.
Delta F.
For example, the ceiling. You don't want to sit down in a building where ceiling is moving in the y direction, right?
You'll die.
Okay. The only reason
building is that?
The only reason ceiling doesn't move in the y direction is because the net force is 0. Lots of force acting on the ceiling, but net force is of course 0.
Yeah.
That's Newton's law number 1. And Newton's law number 2. Raf, can you tell us in the equation form?
Yeah, sigma F is equal to MA.
I thought you were going to say delta F.
F is equal to ma. Isaac, can you explain this one?
Yeah, so essentially sigma F is equal to ma essentially means that the acceleration that an object undergoes once an unbalanced force acts on it is actually inversely proportional to its mass. Now that's a bunch of complicated words, but what it simply means is if an object is more massive, the same force moves it less.
Alright, we're going to of course give you more examples so that you understand it better. Can you tell us Newton's third law?
FAB equals minus FBA.
Isaac, can you explain?
Delta FAB equals...
Isaac, can you explain it?
Okay, so basically what it means is, for example, imagine that you punch the wall. So like I'm punching this table right now.
So force count as a pair, okay.
So if I punch the table, I'm exerting a force on the table, but my hand hurts. Why is that? Well, because the table exerts the exact same force in the opposite direction back on my hand. That's Newton's third law. And the same thing goes for things like gravity. If you have two objects, they can gravitationally act on each other. So the first one will act on the second one, and the second one will act back on the first one.
Speaking of gravity, Raf, can you tell us his fourth equation or universal law of gravity?
The fourth law?
F is equal to GMM over R squared.
Don't mean delta F.
All right, so let's dive in force. Okay, so when we talk about force, what are we talking about? What is force and what force can do? What is force and what can it do? What is force?
Well, a force is essentially just...
anything that push or pull.
Well, that's man-made. So let's divide it. Man-made
But
and
even
God-made.
gravity.
God-made.
But even gravity pulls.
All right. So the man-made or God-made. How many you think out there the God-made force or so-called fundamental force?
Four.
Yeah, but
4 of them.
at the base, they push or pull.
Yeah. So okay. So let's not debate it, Lord, because we know they are God. Well, for lack of a better word, don't ask me prove the existence of God.
Natural.
I can't. Okay, natural. Since you guys don't believe in God.
What?
Natural. Okay. So natural made. Okay. So what happened? Natural made even doesn't make sense. Natural. Okay. So this is Big Bang, right? Big Bang.
But why does it have to be a big...
What time Big Bang happened?
13.8 billion.
So at 0 okay, Big Bang actually happens 0 second, and you are
Yeah, the Big Bang happened 0 seconds
13.8.
ago.
You are 13.8 year since
Hey,
the Big Bang.
Use proper scientific notation.
Yeah, that.
Yeah, 13.8 billion years.
13.8 proper
Oh.
scientific
Oh,
That doesn't
notation.
matter.
Okay.
That's fine.
Dummy.
1.38 times 10
Bet
raised
you're
to
still
10.
thinking about the delta force.
All right, good. All right, so what happened? What happened with those forces? At time when time was 10 raised to negative 42 second, the temperature was actually 10 raised to positive 32 Kelvin, and the energy was 10 raised to positive 22 giga electron volt. At that time, all the quarks were bound together by these four fundamental forces.
Yeah, I
What
can
are they?
verify these values. I was actually there during the Big Bang.
What are those?
Gravity,
Gravity. Number 2,
electromagnetism.
E and M.
Uh-huh.
Number 3,
Weak.
The weak force.
strong nuclear force. Well, strong nuclear force discovered before the weak nuclear force,
Uh-huh.
and E and M discovered before the strong nuclear force.
And of course, the weak nuclear delta
Weak
force.
nuclear force,
Yeah.
and of course the gravity was the one which one discovered 1666. That doesn't mean gravity was born 1666.
1666? That's so evil.
The gravity was actually born at almost 0 second, right? Our physics is not strong enough to take us all the way to 0 second or even 10 raised to negative 43 second. However, our physics is how long? Only 400
It's
years.
miraculous that we can figure out
Yes,
what's happening back then.
that's right.
I mean, we've only existed for the past. This planet has only existed for the past 4.3 billion years.
Well, that's true, but
That's like only one third.
but human civilization is less than
10,000 years.
10,000 years. So,
So
but
being able to figure out with our current models what happens this close to the beginning of the entire universe.
But I don't count human civilization as amount to anything. I count this year more important because for last 400 years, because of Sir Isaac Newton, we have no tools to go all the way back to the beginning. Anyway, at time when the time was 10 raised to 32, the gravity walked away from other fundamental forces, causes the universe
Inflation.
expansion. Inflation, we don't. Yeah, probably inflation is right. Only Alan Gould knows.
Inflation. I hate inflation.
So it started expanding ever since gravity walked away from the other fundamental forces, and it kept expanding for last how long? 13.8 billion years. Okay, so we know how we got the gravity from, or when gravity was born, 0 second. Who gave us gravity? I don't know. Nature. Since you don't want to say God. And who discovered it? Newton. Okay, good. So we know. Oh, okay, man-made.
You don't have to say because you don't want to say God.
That's right.
You're the one who brought up lack of a better word.
Okay, so man-made, push and pull. We can say that, right?
But
Push and
everything
pull.
is push and pull. The strong and weak nuclear forces are pull.
That's true.
EM can be push or pull, and gravity is
No,
pull.
what we are saying that this is man-made push. Okay, can you create gravity?
Well, depends.
Can you remove gravity?
No.
Okay. If you can remove gravity, all the bad people will remove gravity, and you are going to be rushing to the heaven. But I don't.
Or you can create gravity. Actually, this is the equivalence principle. If you are
Yeah, but like
in a
on-
uniformly accelerating reference frame, that's indistinguishable from a uniform gravitational
Yeah, like for
field.
example, the ISS.
What?
ISS.
The ISS. Okay.
But what I'm saying that, would you be able to create the gravity in a massive scale so that you can, then you need to create a big mass like a planet.
I mean, you
To
could
create a-
technically do that.
How would you be able to do that? How would you be able to create another planet like Earth?
Yeah, we are not a Type 1 civilization. Right?
I mean,
We don't have that energy
we
not
can
yet.
create something a bit smaller.
Smaller, like
We just don't find it useful.
yeah. okay.
Why would we create a
All right.
giant mercury
But yeah,
rock?
it is true that we can create electricity, right? Benjamin Franklin thought about harnessing the power of God And this is, look, this is God over here.
And this led to the Industrial Revolution.
That's right. Okay, so
I
what
love
force
the
can do?
Industrial revolution.
What force can do?
Can push or pull.
Oh no, of course. The force can keep what gravity can do.
Pulls.
It can
Gravity
only
can
attract,
can
only
keep
attract.
keep object at rest.
It can push, it can pull, but can it
All
whistle?
right. Number 2. Hold on. Gravity can keep object at.
Right.
Right.
Gravity can keep. By the way, gravity and force are the same thing. Gravity can keep object.
Gravity is a force, but force is not gravity.
That's true. Gravity is a force. Force is not gravity.
Deep.
Well, force.
Yeah, just like when you drop something, it drops.
All right. Hold on. Keep object moving at constant velocity. What else gravity can do? Or force can do? I don't want to say gravity. What else force can do?
A force can accelerate. So
Keep object.
A force cannot make an object go at constant velocity.
You'll see that. Keep
Well, what? But only a net
okay.
force of 0 can
Yeah.
keep it
Keep-
moving and constant.
Keep-
Never mind. I see.
cause
One object.
CAUS cause.
Yeah.
Force can cause object.
Oh, it's like spinning, for example.
Object changing velocity. Number 4. Cause force can cause object.
Change in momentum.
Object change in direction. Or velocity cover the momentum. Okay, now you're gonna prove the first one, RF. So let's say I have 1 kilogram, right?
Well, technically, for example, an object moving at constant velocity that
Hold
still
on.
has force on it, like a
Hold on.
rotating object, has
Yeah.
a changing velocity.
Hold on. I have 1 kilogram, right?
Mm-hmm.
You're gonna come over here, show all the forces acting on it. By the way, velocity is 0. Come over here, show all the forces acting on it. And friction is, by the way, this table is not frictionless. There exists a friction on this table.
Okay.
Okay.
So there is a force of gravity acting down on the box,
Fake.
acting from its center of mass. There is a normal force acting up, and they're equal and opposite in.
What is the size of FG?
FG.
Go ahead. We're gonna use -10 as acceleration due to gravity.
Okay. So 1 kilogram.
No, write the equation first.
Oh.
Don't use the shortcut.
So mg. So m is 1, g is -10. So this is -10 newtons for FG.
Okay, so what is the friction? Where is the friction vectors?
It's not acting because the box is not moving.
Okay, so when box is not moving, even the table with friction, the friction is 0?
Yeah.
Okay.
Yeah.
Alright, great. So this is example of scenario 1, 2, 3, or 4.
Let's see. Scenario 1.
Alright, now Isaac, can you come? Okay, now
See, is the mass on a table at rest?
come. Come. The wood, this is wood. This is also wood. At T1, the wood is 1 kilogram. At T2, the wood is also still 1 kilogram. T1 velocity is 5 meter per second, and T2 velocity is also 5 meter per second. Now, come over here, show all the force acting on. By the way, this is also made of wood.
Well, okay.
No, this is
Wait,
where
no.
you want to draw.
So at T1, there's an additional.
Wait, don't block. I think the camera can.
Yeah, don't block.
There's an additional, much larger pushing force, while at T2.
No. No, they are the all the forces cancel each other.
Oh, so where does the velocity come from? Just
Oh, yeah, it's just there to be.
okay then. So
Can you not block? Yeah.
there still has to be a little bit of force this way.
No, all the forces cancel each other. The object moves with constant velocity.
Yeah, I know.
Yeah. Okay, so find the size. Find the size.
The size of what?
Size of all the vectors.
Okay, so
Sit down.
FG is just equal to mg, which is 1 kilogram times 10 newtons.
Show your work.
No.
Okay.
Only numbnuts like you need to show their work. And Fn is, of course, positive 10 newtons, positive y direction. Now FF, we want F to be exactly equal to the object.
F applied.
Yeah. So FF is equal to mu Fn. Now I think mu is about
0.3.
0.3.
Can you write the equations? Otherwise, how people would know?
Mu Fn.
Is it mu s or mu k?
It's moving, so mu k.
All right.
0.3 times 10 is equal to 3 newtons. And that means this has to be in the negative direction, and this has to be in the positive.
Okay, so now I'm going to ask you a bunch of a question. Isaac, you stay there.
Yeah.
Stay there. Stay over there. Okay. So, can object move, Raf, when the net force is 0, is it possible to can object move with 0 net force?
Yeah, it can move at a constant velocity.
For example, scenario?
So this
Scenario 2.
Yeah.
So can you check scenario 2?
I mean, yeah, of course, as you can see here, it goes from 5 meters per second to 5 meters per second when,
Isaac, hold on. Okay, so Aristotle would be would only understand which one. According to Aristotle, the object cannot move with 0 net force.
Yeah.
Put some light on it. According to Aristotle thought that the object natural state is at rest.
Mm-hmm.
Okay?
yeah, because it was sleeping. It had no energy.
No.
It had
Why did Aristotle thought the moving object? Aristotle thought that moving object you have to continue apply forces to keep object moving. Otherwise, it will come to stop.
Well, I
Because
mean,
This
obviously,
object will never come to stop.
Yeah.
all of this,
Because I mean, Aristotle lived in the real world where there's always
yeah,
a
all of the
friction
objects
between
in
two
the
objects.
ancient Greek world
Yeah.
had lots of friction.
Yeah, I mean,
Wood,
you cannot.
stone,
There is a
sand.
friction over here, but
Yeah.
you don't need net force.
No, but you need an applied force.
I will not apply force, but you don't need net force.
No,
Yeah, but he
what
didn't have-
what
he-
Aristotle was thinking
Yeah,
was
was
you
the
always
applied
need
force.
an applied force to keep an object.
Okay, so that
Yeah.
okay.
Don't
But
mess with my
but
guy
He
Aristotle.
could not idealize it to a frictionless surface because I think at that time
In the universe,
There were no friction.
in the universe, 99%. In the universe, 99% of the thing
Where are you going to get
frictionless.
ice in ancient
Hold on. In the
times?
universe, 99% of the things frictionless. If you go to outer space, some of the things kept moving since the birth of the universe, 13.8 billion years, and moving with
Yeah,
constant
the
velocity.
vacuum of space is frictionless. I think we all know that.
These two scenario, can you tell us how many? Isaac, stay over here. These two scenario, they are okay. These two scenario, they are same.
yeah.
How many ways they are same? There are 5 ways. Can you tell me?
Oh, wait,
It's
what?
over there.
Okay.
It's over there. Sit down. Sit on the board there.
Refab.
Sit in a way that you don't block your fast. Okay. Okay. What is one way they are same?
The total net force in the y direction is 0 for both.
Good.
The total net.
Hold on, Isaac. One way they are the same is net force for both cases. Net force is 0. Second
Yeah,
way
the total delta F, I mean, sigma F is equal to 0.
for both cases. Okay, go ahead.
Yeah, for both cases.
He said that. You.
No, he said in the y direction.
Okay.
Okay. Okay. Y direction. X direction 0. Okay.
How are we supposed to get 5 ways if we don't consider these?
Okay. Okay.
And the total net force is equal to 0.
Sure. Okay, go ahead. No, then there are 7 ways. Yeah.
Okay, great.
4.
I have not helped my case.
Okay.
They both, they both use F equals MA.
No.
No,
Enough.
delta P is
No, we are not talking about delta P.
There's no change in velocity.
Okay, delta V is 0 for
So no change in velocity. He said acceleration is 0 for both cases. Okay, next.
Change in kinetic energy is 0.
No, we are not talking about kinetic energy here.
Okay, let's see.
Fn and G are
No, well, that's not significant. They both are in equilibrium.
isn't that what number 3 is?
Well, the equilibrium is another way of saying they.
Yeah,
their
that's
net
another
force
way
is
of
0.
saying the same thing.
Number 6.
So why keep both of them there?
Equilibrium
I thought we weren't doing-
equilibrium is the
What's the
this
diff-
is the mathematical way of saying it, and this is
Qualitative.
a qualitative way on. And sometimes
What?
no, a student need to understand that. Sometimes in the exam it's written equilibrium, and a student need to understand that when force is zero, it is equilibrium.
But Dad, you're not in the camera.
It's fine. Okay, number 6.
Both of the boxes are 1 kilogram.
They both are an example of Newton's first law.
they're both made of wood.
They
I
both are.
don't even know.
They both are an example of Newton's what law?
Second law.
First law.
Yeah, they're also an example of Newton's second law.
How they are an example of Newton's second law? That force is zero.
Yeah, if you set A to 0 in Newton's second law.
Excuse me, I'm making it for my student.
Okay.
If you keep making fun, I cannot use it for my student.
But
This is an example of Newton's first
how am
law.
I making fun?
No, isn't it example of Newton's first law? How it is an example of Newton's second law?
Something can be an example of two laws at once.
No, you
Not
try
one
to
law.
confuse people. How?
Just keep it simple
Keep
for,
it
for the physics students.
How? If I say this is Newton's second law as well, how I can help a student?
Okay, sure.
Would that be helping?
No.
I mean,
If I say this is also Newton's second law, how that gonna help? Okay, so let's go to the next one. What is the eraser?
the eraser should have been behind me.
Okay, so all right. So the next one is
Wait, there was 7. You said 7? Okay.
I'll forget it. I'm not doing the seventh one.
velocity is 0. Velocity is how much?
0.3.
0.3, and velocity is 4.5. Okay, when the velocity is 4.5. Okay, so who wants to do that? You're gonna draw the Isaac. You're gonna draw this one.
Wait,
Free
velocity.
body diagram when velocity is 0. Right here.
Velocity is 0.3. You
Just
mean-
0. Velocity is 0.
No.
Oh, velocity is 3, right? Because
what?
3 meters per second.
The time is
Ah.
0.3.
Yeah, because time is
Oh.
0.3. Yeah, yes.
This is coming from the same guy who said delta F.
Go,
He's
go.
not credible.
Go.
Hey, I'm incredible.
F
Go.
net equals delta F chat.
Go!
Okay, fine, I'm sorry. Okay. And I have one more stunning conclusion to make.
Isaac.
Wait, no. Since this is equal to this, and we know this is equal to MA, then clearly we have, which means that M times jerk is equal to impulse.
Okay. All right. Okay. Good. All right. So again, this one is when you're holding the book. This one is when the book is in,
Free fall.
and this one is when the book has
Hitting
maximum
the ground.
And this one is when the book is holding you.
velocity.
Yeah.
That means book touched the ground,
Mm-hmm.
but didn't come to rest.
Yeah.
And this one is when the book is come to rest.
Easier.
Okay, go ahead.
Oh, okay. Free body diagram.
Free body diagram.
Go ahead.
Okay. Well,
How much?
it's equal to.
You said 2 kilogram.
Yeah. So.
Raf, you do the next one.
Okay, I'll do the next one.
Isaac, where is the FN? The book is at the hand.
Oh. I thought it was when you just dropped it.
Basic
So.
physics. Okay, can I give it a shot?
Okay, delta N man. Delta F man. Okay.
What is the FN here?
It's dropping.
Good.
I'm not stupid. Stupid.
FN.
That's here.
No, but this is when it has a max velocity and just touches the ground. Can we?
I think he got
This
it.
is the moment before it touches the
No,
ground.
it
this is when
does.
it just touched the ground with a max velocity.
Big FN. It has a big FN.
Yeah.
Okay,
Yeah.
Fine.
Did you forget what you found out last night?
Yes.
Wow. Goldfish.
How much?
How do I know?
Okay, go. Raf, you find it. Isaac, go. Sit down.
I don't.
It depends on the coefficient of restitution, which we
I mean,
don't
I-
know.
0.6.
Yeah, I actually.
Who does it?
We still have to assume how long
I can
it
try
takes.
to
for the
model
book
it
to-
Yeah.
as a harmonic
So,
oscillator.
yeah.
How long does it take to? No, it does not follow a harmonic oscillator. How long does it take for the book to bounce off of the floor?
Let's say 0.01 seconds. Okay, so.
Okay, you're
okay,
a very smart
let's-
man. You're a very smart man.
Sit, Isaac,
Sit
sit.
down, sit down.
Isaac, sit.
Let-
Raf,
let-
don't block.
Oh, okay.
You can erase everything over there to do that. So Raf is gonna find Fn,
Okay.
which is
so,
not gonna be easy.
Okay,
Yeah,
so let's
it's gonna
say
be hard.
the time it takes for the book to come to. Oh,
Yeah.
He's actually a real freakster.
Do it
So-
nicely.
okay.
Did you say anything bad? I have to.
No.
No.
What did you say? Okay. Okay. Alright, let's go.
So delta t is 0.1 seconds. Let's say that's let's make it realistic. So this is how long it takes for the book to come to rest in the ground, right? So when the book just hit the ground, it's coming in with a velocity of
4.5.
4.5 meters per
And
second.
then it's gonna go approaches to
Bro's got the
zero.
goldfish
Right.
memory.
No, good. And then its final velocity is 0 meters per second. So from this and VF is VI plus AT. We have VF, we have VI, we have T. We can calculate the acceleration.
Oh, yeah.
So let's do it. Please sit back down.
You
Mr.
can also
Mistake
use
Man.
impulse.
Wait, what?
Impulse.
No, we are not.
Oh.
The impulse is not. We did not cover impulse yet.
Okay.
That's a good idea. But
I have the impulse to set you up.
so VF is 0,
Jerry loves you,
VI
baby.
is 4.5 plus T. What? I forgot what I said. So okay, so now we have to do.
This guy's so dumb. Can you do that in your head, little boy?
So.
You're freaking stupid!
So it's
Oh, that's pretty big. Okay. So so this is the.
If you do have the stupid,
This is the net acceleration of the textbook when it first hits the ground. And as expected, the net acceleration is in the up direction
yeah, and
because
of
the
course.
book is slowing down. And we know.
Isaac, sit down.
Look at Jimmy.
Isaac, sit. Okay.
Okay.
He could drop on you at any time.
And we know the gravitational force on the book. Let me write it here. The gravitational force on
You
the
can
book.
use black as well. Otherwise, you
Yeah. Okay, and what is the mass of the book? 2 kilograms.
yes.
Okay, so let's say G is minus 10.
We don't need drum roll.
So minus 20 newtons. Okay, so this is the force of gravity acting downwards, right? And we know what the net force on the book is. Let's
Yeah,
write
we
it
know what
over
delta F is.
That's very funny. So F is equal to the force, the normal force minus the gravitational force, and this should equal 450 meters per second squared times the mass of the book, right? The mass of the book, 2 kilograms.
900.
So this is 900 newtons. Okay, we know the gravitational force on the book is 20. Okay, 20 newtons. And so that means if we solve for the normal force, we will get 920 newtons. Now you can ask yourself, is this reasonable?
Yes.
Is this reasonable?
Yes.
And how can we check if this is true?
Yes.
So one way we can check that this is true is by changing the time. Okay? So intuition tells you that if the time is longer for the book to come to a rest,
Then it's
should the normal force be greater or smaller?
smaller.
Why?
That's why.
Because less
Yeah.
force is being exerted over a greater period.
That's why. If you have a
Okay.
seat belt, you don't die.
Right. So the normal force should be less if I increase the time, right? So let's say I increase the time to 1 second.
Oh, that's
So-
forever. Normal
Then
force
that's like
would be-
9
Okay.
units.
Normal force would be
Okay.
almost zero.
Okay, let's say 0.1
Not
second.
almost zero. It's gonna be almost.
Almost gravity.
Yeah.
So let's say I make it 0.1 seconds. Let's see what happens. Then the acceleration would be 45, and so this would be 90 newtons, and so I would have 92 newtons for the normal force. So
if you do have the stupid,
what? 90 plus 20 is 90. 110
Wait, no. We got a new quote.
That's not what I meant. I
guys.
misspoke.
90 plus.
I just had a Joe Biden moment.
He had a Joe Biden moment. Okay.
We found Bari, and what date is it? November 28th.
Our target day.
Okay, I got
All
roasted.
We
right.
got a new.
Okay.
Yeah, just like a turkey.
So it makes sense,
Yeah.
actually, the answer we got.
All right. Great.
Oh, what if we make the time? Oh, let's make the time bigger and bigger. Let's see.
What if we make the time 1 billion
Then
years?
this would be. If we make the time 1 second, this would be 4.5.
My God.
And so then this would be 4.5 times 2, which is 9.
So the
and 9
answer
plus
is
20
is 11, right?
29 newtons. Okay.
Not 20 and 20.
Yeah, 9 plus 20 is 29 newtons. Yeah, it's 29 newtons.
That's correct.
And so you're seeing we are approaching the gravitational force. What if, let's make it even bigger. What if we make it 100 seconds?
Okay, Rifat, you don't have to make it this dumb. It's literally 20.
Yeah. In fact, let's make the time. Oh, in what case would the time be infinity? There is a physical
It's just
case.
20.
No, what case will the time be
That's-
infinity?
It's standing on the floor.
No, it means the book doesn't bounce.
This guy,
Right?
why did he have
You have to
that
have.
piece of wood?
Yeah, you have to have a
So-
mattress.
Bro, you look
Yeah.
like the
Okay.
freaking terrified.
Okay. All right. Okay.
So then
that's,
you get exactly 20
all right.
newtons.
Okay, that's
the
fine.
normal force.
Okay, that's fine. Okay.
90 plus 20 is
Okay.
90.
All right. Now next one.
Wait, no. I got one more quote.
Oh, you didn't do. Oh, you did it. Okay. Good. Sit down. Sit.
Wait, no, the quote.
Sit.
Don't worry, I'll
Okay.
say it again.
So the last one. What would be the example that
You sit on
force causes?
We've had not on camera.
Yeah. Causes what? Change in direction. Force causes change in direction. Can you give an example?
I got
Sit down. The Earth, the Moon, orbit. Okay. So force
This
causes.
guy's
I'm
such a
gonna.
party pooper.
No. I'm gonna give you an example. You solve it. Okay. You're gonna tell me how many things you notice. This is location A.
What the
This is location B. All right. You're gonna tell me how many things you're gonna notice. So R is 10 meter. Velocity is 20 meter per second.
This guy is riding on a planet of radius 10 meters.
No, not planet. It's a car moving.
Oh, it's a track.
Yeah, it's a track. It's a circular path. So the velocity is how much here? 20 meter per second. Velocity is how much here?
Also 20.
20 meter per second. Isaac, can you tell me how
Wait, I
many?
have an idea for how you can do this with the buggy. You know what it is?
No. Yeah.
Wait, no.
Let me give you all the information. You always can do after this one. Let me finish this one. Sit down. Okay, sit.
Aww.
Oh, okay. Sure.
If you just take the regular buggy, it obviously moves in one constant direction, which is the direction you set it. But you can demonstrate circular motion. How? You
Put it on a rope.
make a track, put it on a rope, and the rope's tension force will act as the centripetal force on it.
I just said put it on a rope. You stole my idea.
What?
Okay.
I'm the one who came up here.
Cool. Oh, that's right. Okay. Now sit. Can you tell me how many things you notice here?
I mean, lots of ink.
At least At least one thing you notice.
Okay.
The velocity is gonna
magnitude
change.
of the velocity is constant, but the direction of the
No.
velocity changes.
Oh my
No.
god, I didn't know that.
You saw that velocity is perpendicular with respect to the force. What is the
And
next thing?
perpendicular with acceleration.
Velocity perpendicular. Okay. You also notice that acceleration keeps changing. The direction of the acceleration keeps
Yeah,
changing.
changes in a correlation to the tangential velocity.
Do you see the constant velocity at location A?
No.
Well, it's constant
the
speed.
magnitude of the velocity. is
Constant speed.
So, is this a good example that force can cause? Even the velocity is constant. Force can cause What?
changing
Acceleration.
Yeah.
No, the
by
velocity.
changing direction.
The velocity is not constant. The speed is
The
constant.
speed is constant. Why velocity is not constant? Because
Because-
there is an acceleration.
Yeah, because
And-
the velocity is a vector and it has direction.
That's right.
If the direction changes, it's not the same vector.
So we can do,
Good job.
so
So
two thing. So
I'm
two,
explaining to students here, you dumb.
so two thing.
Yeah.
Two thing give rise of acceleration. One is change in velocity,
Yeah.
and one is change in
Direct.
direction.
Yeah.
Two
The
things.
acceleration causes these two, not these two things cause acceleration.
Change in direction can rise to acceleration,
No.
as this case.
Acceleration causes these two. It's not that these two cause acceleration.
Very good. Okay, so acceleration causes change in velocity, and acceleration causes change in
Direction.
direction. Displacement. Okay.
Um,
Can you find the acceleration?
what?
Yeah.
I
I
mean,
can do it. Yeah.
the acceleration.
Let me help you out. V squared
I'm not done.
over R.
I am not. Wait. Okay.
You got a question, the basic mechanics?
Alright, so.
There's no need for omega R. There's no need for omega
Wait,
R.
this is the most intuitive definition, but of course, since omega is V over R, you get the more common definition that you'll probably see in a reference table. The centripetal acceleration is equal to V squared over R. So, V squared, while V is obviously equal to 20, and we all know 20 squared is equal to 400. And so, delta F, let's see, R's. You're such a stupid. This is 40 meters per second squared.
All right, fine. Raf, can you find the force?
Yeah.
So this is acceleration is 40 meters per second. Raf, can you find the force?
Mm-hmm. Okay. So,
Isaac, is it done?
let's see. So the force is going to be the centripetal force.
Newton's second law, right?
That's right. M times the centripetal acceleration. M is 1,000 kilograms. 1,000 kilograms. And centripetal acceleration is 40. So this will be 40,000 newtons of force.
Okay, so what
Yes,
causes?
1,000 times 40 is
Okay.
4,000.
All right, now you're gonna draw the free body diagram. At location I, Raf, you're gonna do at location A. Isaac gonna do at location B.
Okay.
Go ahead. Raf,
Okay.
go.
So
No,
What?
only the car.
Oh, okay.
Only the car.
Okay. So okay, here's the roller coaster underneath, and so first
Roller coaster.
there is gravity acting down. There is the centripetal force. This
What
is not.
what is the
not-
source of centrifugal force?
The gravitational force.
Friction.
Oh,
Friction.
Weird.
Friction.
It's riding on a track.
Friction. 100% friction.
What?
Source of the centrifugal force is friction because this is a road.
oh, that's,
This is a road. This is not a planet.
No, it has to be like a.
Newton first law represented by which two scenario?
object at rest
Wanting to.
and object at constant
Newton's
velocity.
second law represented by which two scenarios?
3 and 4.
Now let's go over Newton's third law. Okay. So what is Newton's third law? Can you remind me?
Any action has an equal and opposite reaction.
Okay.
For
So
example-
F AB is equal to negative F B. Mr. Bari is 60 kilogram. Okay. So far so good. The Earth is
10 to the 23 kilograms.
a little bit bigger than Mr. Bari.
24.
Okay.
23 less than
24.
Was last time you were checking during the birth of the solar system or something?
The Earth was forming at that time, the baby Earth. Okay. All right. So far so good. Now, Mr. Bari crouches. In order to jump up, he has to crouch. So CROUCHS. 0.2 meter. Mr. Bari jump off the ground. 0.8 meter.
Thinking of something so fun.
Okay. So now, can you tell us? This is Earth, and this is Mr. Bari. All right, so this is going to be Newton's second law, third law, action and What is this one? Can you tell me what is this one and how much? I'm gonna put it over here as well. How much is this one?
600 newtons.
Good. What do you call this one instead of calling it Fg? F on Bari by
Earth.
And similarly, there's an Fg exerted by you on the Earth.
Oh, okay. So what are you gonna call? So this is Mr. Bari, and this is what?
On the Earth, you are exerting. a
This is
gravitational force.
Fg, and that
But-
is how much? 600 Newton.
But of course, unless you're really, really, really fat, it's not going to move.
So instead of Earth, instead of Fg, what are you gonna call it? Yeah, you can call
FEB.
Fg 600 Newton, or Fg you can call force on Earth by
By Mr. Barry.
Mr. Bari. Okay, that's all, or there are more?
There's also normal force.
Not
No,
normal
but that's
force.
not a force.
Or
Oh,
the-
you fell for your own fallacy. That's crazy. That's
no, I'm
crazy.
not saying it's a third law action reaction pair. I'm just saying that there's a contact force between the
So
Earth and the
the push.
moon.
All right, push.
The moon.
Mr.
The
Okay,
moon.
hold on.
Mr. Barry is the moon.
Mr. Bari pushing the who?
And wait,
the-
there's
Push
a
that.
normal force on the moon?
Mr. Bari push the Earth. Instead of pushing, what can you say?
force of.
You mean pull, right? Because it's-
I have to push in order to go up. I
Oh,
have
you
to
mean
push.
jumping.
force of
Yeah,
crouch. Crouching.
Not crouch. We can say a
Or-
kick. Kicking?
Okay, yeah.
Kicking the Earth.
You're propelling yourself up. Just jump.
Oh, so Mr. Bari push. Oh,
I mean, technically, it's
Force.
a crouch.
okay. Force on
No,
Earth.
crouching is the action of doing
Doing
this.
this, yeah.
Yeah, but isn't that what we're doing?
No, we're pushing ourselves like that. Oh crap!
No, but that's multiple things.
Okay, so Mr. Bari, force on Earth by Mr. Bari. Again, I'm saying the same
Yeah,
thing.
that's why you can't use the same terminology.
Oh, prime.
Okay.
That's not how you write prime.
Or you can just put one prime on top. You stole my
Okay.
idea.
Okay, prime. Okay.
You
Okay.
stole my looks.
Shh.
There was nothing
Okay.
to steal, so-
God
Okay.
damn.
So now, what is this one?
And I stole your intelligence.
What is this one?
90 plus 20 is 92.
What is this one?
Force of Mr. Barry on Earth.
Okay. Now, see, people think that since action reaction is always the same, how Mr. Bari ever gonna be 0.8 meter above the
I
ground?
think this one should be force of Mr. Barry on Earth because this one is pushing down.
Force on Earth by Mr. Bari. Yeah, force on Earth by Mr. Bari.
It goes in
Force.
English order.
Force
Force on Bari by Earth.
God damn.
but
you
force of Mr. Barry on Earth is down, right?
No.
Because
the force
because
on
he's-
Earth
he's
by
pushing
Mr.
down.
Barry, Stu.
No, this is prime.
Okay.
Okay, so now you're probably thinking, the action reaction gonna cancel. How Mr. Bari ever gonna move? Let's see what I mean. This is the fallacy.
Wait, no, wait.
Hold on. This is the fallacy.
The fallacy.
Yeah, this is the fallacy.
Wait.
And the what? Hold on. Say it. Okay, this is the fallacy. Fy is you're gonna say, all right, this is 600 watt.
Newtons.
So Fg,
Yeah.
and this is negative Fg.
Yeah.
This is positive
FBE prime.
positive Fbe, and this is negative
FEB. They
Feb.
both have primes.
Yeah, they both have prime.
Yeah.
Is equal to.
0.
So you're gonna say this is equal to 0.
Mm.
So Mr. Bari never gonna move,
What
and that
the
is
sigma?
completely wrong.
Mm.
And that's not how you do it.
Mm.
Can I do it?
Sure.
Yeah, so the thing is,
That's not how
this
you-
is the total net force on the entire system. But,
That's not even a thing.
yeah, I know.
Okay.
It's the sum of the net force that's acting on each individual. But each individual...
Why this is bad? You did not explain.
This is bad because it's assuming that the action-reaction pairs act on one thing. When in reality, the force of Earth on Mr. Barry acts on Mr. Barry, and the force of Mr. Barry on Earth acts on Earth.
Okay, so can you circle two components?
The fact that it doesn't move only works if the net force on one object is 0, not if the sum of the net forces on two objects
Very
is
nice.
0.
Now, can you circle two forces that propelling Mr. Bari to the sky? Circle them. Circle two vectors. You have 4 vectors. Can you circle 2 vectors that will propel Mr. Bari to the sky?
This one and that one. No.
I mean,
That's not acting on Mr. B.
Okay.
This one.
Yeah, that's right. That's
But that's
true.
gonna bring him down.
Regions.
Not bring it
No,
down.
come on.
No,
FG?
No, they
No.
both act together.
They act together, and then you'll see that.
Yeah, that's the net force. But you're saying which two forces
I mean-
both propel him?
Well,
Okay.
there's only 2 forces that act on this.
Yeah, there's 2 forces act on Mr.
Not
Bari.
many options here. There's only one way you can choose.
Okay, 90 plus 20, the guy.
Okay, go ahead. Let's
I'm
see.
not a math major, sorry.
Let's see.
Okay.
Okay, fine, delta F guy.
Okay.
Not a
Can you erase it?
Wait, what? He's literally lying to our faces.
Okay. Make a space.
Weird.
Make a space. Erase your earth and Mr. Bari on the diagram. Okay, now do the
I thought
math.
my art was good.
Yeah. It's good. You have a good artistic ability, but we don't need Picasso. We need Einstein.
Sus.
Okay, sure. I'll do.
Okay, what are we doing?
No disrespect to Picasso.
No.
Picasso will probably.
Okay, Dr. Capel, what are we doing?
When Picasso see
No.
a banana in a
No.
duct tape, a banana in a duct tape is $6 million.
I think-
he will probably commit suicide.
Yeah, that's what I was gonna say. If he saw that, he'd probably kill himself.
All right, go ahead.
Modern Picasso versus real Picasso.
No, abstract art in Picasso's day. Abstract art today.
I don't think that was $6 million Picasso's time.
But it was at least at 10,000.
And now this is how much?
I mean, now
$6 million banana on duct tape.
it's 6 million?
I think
Yeah.
You mean 25, right?
25. It's getting bigger every day.
I think the price.
No, that was the price in 2018. It's now more.
Inflation really increased food prices.
All right, let's. No. That was a good joke. Okay, all right. So how are we gonna do that?
Someone put a pineapple on an empty art stand, and the next day it had a glass case on it.
All right. So how are we gonna do that?
What are we even doing?
Oh, how much? Okay, what is the pushing force? What is the size of this push? First, put the equation.
It depends on how strong you are.
Okay, sure. All the information is there. First,
No, it isn't.
yeah.
Oh, crouch 0.2, height 0. Okay.
First, put the equation.
I delegate this to you.
I'll do it.
I can do it.
So Fy is equal to what? Or F push is equal to what?
What?
Or maybe Fy, let's see, Fy is equal to, or F push. F push is equal to what? F.
On, Mr. Barry, is
yeah,
that
F.
BE prime
FBE prime
minus FG?
minus Fg, that's it. That's F push.
Okay.
So then F push is, then we can say that F push plus Fg is equal to
FBE prime.
FP. Okay, so push is actually what? The push is actually mg plus a, right?
Mm-hmm. It's like an elevator.
Yeah, it's an elevator. So here we can say the diagram.
It's like an 8-1 machine.
This is A, this is B, this is C. At A, velocity is 0. At
Wait,
C,
so why do you look like a less than sign?
Because he's crouching at this
crouching.
I mean, I don't see anyone who looks like this when they
Now,
crouch.
can you draw crouch? I don't know.
Yeah,
I can't draw.
I can probably.
Don't let this guy draw, bro. He looks like he's reverse twerking. What are you drawing?
He's just crouching. Looks like a spider. That's disgusting. He will
I
not
didn't know a
have
spider had 4 legs.
Okay, now BF
a
squared.
deformed spider.
BF squared is
Wait,
VI
so
squared
we're deformed
plus.
spiders because we have 2 arms
Hold
and
on.
2 legs?
And BF squared is equal to VI squared plus 280. Now, if I put over here 0.8, what I have to put over here then?
Shingi Masanga.
So Vi will be 0. Oh, I can.
No,
I can,
no,
I
not
can-
BI will be 0. This is 0 then. VI you finding it. 2 is negative 10. Okay? So then what is that? VI squared is 16, B is 4.
Wait, wow. So
Oh, so this is his velocity at B.
Yeah.
At B.
So you've been losing knowledge ever since you went to Brown. You were doing way
you
better
need
in the
to
old
find the
lecture.
velocity here.
No, velocity is 0.
No, I mean.
Yeah, this is like fraction of a second it takes.
I mean, find
from A to
the
B.
acceleration.
Acceleration, right.
Find the
Did
acceleration.
you get
So-
dumber from going to Brown?
Do you know
So,
what Feynman path integrals are?
No, before you went
Yeah,
to
the
Brown,
square is
you
how
only
much?
dropped a dumb quote once every 2
4 squared
episodes.
is equal to
Now
0
you dropped
squared
3
plus
and 1.
AD.
2. A,
We
D
don't know,
is
yeah.
0.2.
D is, yeah.
So how much? A is 40.
I'm just,
Okay.
oh, wow.
So F push is,
Back-
M is how much? 60. And this is 10. It's not negative 10 anymore.
No,
Yeah, it's
A
negative
is,
We negate it here.
is
so
40.
This is 10 and this is 40, right? Is that right?
Yeah, so
Why we don't put negative 10?
Wait, I think.
Why we not putting negative 10?
Because
Because we
we
already
just negated it.
Negated it, yeah.
Wait,
So
I
50.
have
So
a-
3. So,
I have a doubt.
so 60 times 50. How much?
3,000.
3,000. So this one is 3,000.
But I think this 40 includes.
If you
No.
have-
No, this is
the
net acceleration, yes.
Yeah. So the net acceleration
It's
should
40.
include gravity, no? Or
No, because this has to go
Oh.
against gravity to produce such a net acceleration. Do you get it?
No. I'm saying that the net acceleration here
It has to go.
is including gravity.
Yeah.
So
Yeah,
the acceleration due to just his legs is 50, but minus the 10 from gravity gives you 40. I think.
yeah, but we're calculating the force produced by his legs,
Oh,
which is
just
due
the
to the
push.
acceleration.
Oh, I think that's right. I think that's right.
Boom!
So this is 3,000
That's
Newton, this is 3,000
He
Newton.
got dumber.
That's right.
So,
No!
so
he
if we come back over here, we write 600, negative 600, positive 3,000, negative 3,000, and that's 0. So how we ever jump up?
Because they're acting on different objects. The forces are on different objects.
Okay.
That's crazy. I didn't know that.
All right. Okay, so that's Newton's third law. Now we're going to do Newton's fourth law, and
What?
that is universal law of gravity. You're going to show.
Can I?
Yeah, the force. That's
Yeah, you
it.
can do
That's
it,
the last
yeah.
one.
You can do it.
No, can I leave?
No, that's the last one. What is the last one? Newton's
F
universal law of gravity. F.
is
G.
G and M over R squared. And G
And-
is 6.67 times 10 to the minus.
Memorization is a crime,
Okay,
man. We're
so-
gonna have to lock you up.
So,
Hands
guys.
behind your back.
So guys, hold on. This is
Oh.
this is Earth.
Uh-huh.
This is Earth, and this is Moon. Okay. Now,
He just made a primal distress signal.
what is the name of this one? F
Force
on
of the moon on the earth.
force on the Earth
What the
by Moon.
force on the
Okay.
What
If,
was that voice crack?
if this one is 10 centimeter, this one must be 1 centimeter. Is that right?
What are you talking about?
Raise hand if you agree, and thumbs down if you disagree.
I agree.
The moon is 100 times
Good.
less massive.
It has to be the same.
But that wasn't the mistake. The units were wrong.
No, that
Unit.
has to be the same. Okay. Force
Guys, I
on
didn't know force was in newtons.
force on what? Moon by
the earth.
Earth. Okay. So the Earth is how much? 6 times
yes, force.
10
Measured
raised
in
to 24.
centimeters.
Earth is Moon is 7.35 times 10 raised to 22. Radius between the Earth and Moon is how much?
3.84 times
Quarter
10 to
of a
the
mile.
Good. 3.84
miles.
times 10 raised to what? 8.
Listen, it's not a crime if I commit it.
Okay. All right. So, G. What is G? 6.67 times 10 raised to negative 11.
Memorization is a crime, guys. We're gonna have to lock you up.
Oh, Isaac, explain where this come from.
No.
Rafat, explain where this come from.
Kindly no.
Oh yeah, I can explain.
It's experimental.
You want me to explain Cavendish's experiment between?
Yeah, in 2-3 lines.
Okay, yeah. So okay. So around the 1600s. So when Newton published his universal law of gravitation, he didn't actually.
1685 or.
Yeah, around 1600s. He didn't actually know what the numerical value for G was. So afterwards, a scientist named Henry Cavendish calculated what G was by doing the following experiment. He had
You're blocking Isaac.
he had two steel. I think it was steel or metal. I don't remember the
Steel or metal?
one of them. And
Steel is not a metal, guys. We just learned this from Revath Albert Bari, one of the greatest scientists.
physicist, not scientist.
Can't take.
Okay,
Okay.
let's go.
So each of the
I
balls
can't
was-
take this anymore,
was
guys.
1 kilogram. So now if you plug this in, and the distance between the two objects was 1 meter. So now if you plug this into Newton's law of gravitation, then you get G times 1 over 1 squared, right? So why did he choose all of them to be 1? So that the force would just be G. So that if he can calculate, so then what Cavendish did was he calculated how much, so this was like on a string, it was like on a torsion, and he calculated how much the gravitational force exerted a torque on the two balls, right? So if you know what the torque exerted on the balls is, then you can calculate what the angular acceleration of the balls is. From the angular acceleration, you can get the linear acceleration of the balls. From the acceleration of the balls, you know their mass, so you can get the force on the balls. And so now if you know the force, then you know G.
I'm not gonna lie, those are some balls of steel.
So that was Cavendish's experiment, and it was very difficult because to actually see two objects attracting each other is very tough if they're not large. So what he did is he actually had a little telescope, if I remember correctly. He had a little telescope to see how much the distance between the two balls changed when gravity
Very
acted on them.
painstakingly he did it.
Yeah, so
Isaac, you're gonna find the gravitational force, the size of these two vector, and that's it. That'll be it.
Where is I? Oh,
where is I?
yeah.
Do it nicely.
I is actually right over here. Okay, so
Do it nicely. FG is equal
let's
to.
see. FG is equal to G, which is 6.67 times. Oh, that's memorization. I guess I gotta lock myself up. And one is he's already calculated. Let's go, calculator boy.
You know, I'm not ashamed of that. I'm actually proud.
Yeah, 'cause that's the only thing you're good for.
I can calculate Feynman diagrams. Can you?
Oh, who needs that useless crap? I can
uh,
calculate the multiplication table of the third symmetric group. Can you?
So I'm not good at calculating useless things.
Yeah, the Feynman diagram pretty damn useless to me.
Not if you ask the 1965, 1967, and 2004 Nobel laureates in physics.
Not if you ask literally every single mathematician who's worked in group theory before.
If you keep fighting, how are you gonna make progress and help humanity to? Okay.
Did did the Bernoulli brothers like each other? No. Did they help humanity? Yes.
Okay. Sure.
I already wrote the answer while you were talking with Dad.
Yeah, because you got the calculator.
No, I did it in my head.
I did it in my head. You probably come out with some stuff like 3 million. You're the guy who said 90 plus 20 is equal to 92. You cannot be trusted to calculate stuff in your head.
90 plus 20.
What the fuck?
I call him Sakuntala Devi of 21st century. No, you're not gonna call him Sakuntala Devi of our time.
This isn't Shakuntala Devi. This is Sakuntala Developer.
All right. Okay.
Walmart Shakuntala. Harmony Bites Shakuntala Devi. He literally got the blue logo.
All right. Go ahead. Oh yeah, it's 2 times 10 raised to 20 Newton. Isaac, put the size over here.
So this is 1.99.
No, 2. It's a big number. It doesn't matter whether it's okay. So
But
now,
then is 199 equal to 200?
okay. All
I'm
right.
joking.
All right. So can you draw the velocity vector and acceleration vector
The velocity vector
as moon moving around the earth?
is perpendicular this way,
Acceleration vector.
is going this way.
So it's the same as car moving around the circle. All right. So yeah. All right. Come. All right. So the biggest discovery today for us, Raf.
So I discovered that just because the force is acting on an object, that does not mean the object is accelerating. It could mean the object is moving at constant velocity. So
Or at rest.
or at rest. And we saw that for the case
Force,
of
lot of force acting on it, but
Right.
it's not moving. If it is moving, then we all be dead.
Yeah.
I discovered that even if an object is moving on a table, if that table has some friction, you still need to apply a constant force in order to keep it moving at the same velocity.
And that
I'm glad
is,
you
yeah,
discovered that.
and that.
You want to throw hands?
What else you discovered?
I also discovered the gravitational force between the Earth and the Moon is the same as the force between the Moon and the Earth. I used to think that the
And
Earth
one
pulls
more
on
thing
the
he
moon.
discovered was that 90 plus 20 is equal to 100.
All right. Apart from joke, what was the most challenging things we did today?
Calculating 90 plus 20.
No, apart from that.
Apart from that, it's a legitimate challenge.
Yeah.
Staying focused.
Let's see, I think this calculation was straightforward. But the calculation we did with the normal force
I
was
think that
different.
one was like dropping something, right?
This has the most numbers, so I think it's the most complicated.
No, the dropping something. When book at your hand, Newton first law, because net force is 0. When it is falling, Newton's second law, because net force is not 0. When it is about to hit the ground or maximum velocity, it hitting the ground with maximum velocity, is it Newton's first law? Of course not. Newton's second law is because there is a net force at the y direction. And when it comes to rest, velocity is 0 again. It's Newton's first law. So I don't know.
The crouching problem was also difficult.
Yeah, crouching problem.
Crouching problem was tough, and you might expect that the net force on the man will always be 0. Because
Oh yeah. If you
because
add them up,
all
if you add them
forces
up,
should be 0.
if you add them up, right?
But
600 minus 600 plus 3000 minus 3000.
That's clearly 2.
and also finding the
Oh no, that's right.
the-
A
yeah.
physics student will say, okay, all right.
Yeah.
Hey, give me
600
the cap.
600 minus
600
plus 3000
Yeah.
minus 3000.
Yeah.
How am I ever gonna jump up?
I was confused about that last night. I don't know why I'm walking. How I can walk.
No, I mean, of course he's exaggerating,
This is
but
so